Why shouldn't we be worried about Skynet? Why shouldn't we be worried that every job on Earth is going to immediately be taken over by things that are stronger and smarter and even more creative than we are? Why is everyone all wet with these fears?
So I'll tell you the difference between what people think and what actually is by means of an analogy between a phenomenon which was quite the thing in Germany 50 or so years ago. It was a phenomenon involving a horse called Clever Hans. Clever Hans was the star of various circus entertainment shows, and people would pay money to see Clever Hans calculate before their very eyes. So you would give Clever Hans a problem to solve, so multiply 19 by 3, and Clever Hans would bang his foot, his hoof, his clop, 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 and give the answer. And everybody was amazed that Clever Hans could answer these arithmetical puzzles immediately, so they paid more and more money. But then it was revealed that the whole thing was a scam. So in fact, Clever Hans was not answering any kind of mathematical question. What he was doing was reacting to small twinges on the part of his master, when to start clopping and when to stop. Now, that means that the horse was not exhibiting arithmetical intelligence. It was exhibiting sensitivity to its master's voice. Now, similarly, ChatGPT or any of the other large language models is not exhibiting intelligence. It's exhibiting its ability to carry out various kinds of operations with mathematical algorithms.
Hello, and welcome to Haman Nature. I am Adam Haman, and I'm very pleased to be joined by the authors of this book, Why Machines Will Never Rule the World, Artificial Intelligence Without Fear. That's a relief, fellas. Please welcome Jobst Landgrebe and Barry Smith.
Hello, thanks a lot for the invitation.
Very nice to have you. It hasn't come out yet as we record, Jobst, but I interviewed you about your book, The Hype Cycle, which was brilliant, and the viewers will have seen it already, so thank you for that. And I'm even more excited about this book because everybody has notions both smart and foolish about what AI is, what these LLMs are, what is coming in the turbulent future. So thanks for doing this, and welcome, Barry. I'd like both of you, if you don't mind, if you're not too self-conscious, to give a little brief bio, who you are, why do you know anything, and why should we listen to you?
So my name is Jobst Landgrebe. I studied medicine, biochemistry, and mathematics, but I was always also interested in philosophy. I worked until I was 35 in the academic world, and then I switched into a business where I worked on AI ever since for more than 20 years, and also scientifically. So since a quarter of a century, I work on AI and utilize it to make a living. So that's my qualification about AI. But when the current AI wave started, my customers were asking me why I wasn't doing and promising certain things. And I said, because they are impossible to do. And then there was one customer who was a mathematician who really asked in the hard way. And then Barry and I decided to start writing papers about it by bringing together mathematics and philosophy and neuroscience, biology, physics to answer these questions. And that's how our collaboration started. And that's how we wrote this book, which is now just appeared in the second edition.
So my name is Barry Smith. I studied mathematics and philosophy, worked for 20 years in an area called ontology, which is kind of metaphysics. And at the turn of the millennium, I was approached by various computer scientists who were using my work in ontology as the basis for new kinds of treatment of data. Basically, ontologies were being used to create homogeneous data systems out of heterogeneous data. And I've been working in that field ever since, partly as a philosopher trying to throw some philosophical common sense into the mix, but partly also as a collaborator with various people in multiple different areas, including biology, medicine, manufacturing industry, intelligence. So I am working now mostly with people on the defense and security side of things. I met Jobst for the following reason. So my work on ontology in the biomedical domain exposed me to scams where people were using new systems for dealing with biomedical data in order to make money. And the data that they produced was deliberately designed to break the systems that they were used on. And the owners of this particular scam were the people who were paid to come and repair those systems when they broke. So it was a brilliant scam, and I started a blog, and that's when I got in touch with Jobst, and we've been in touch on and off ever since. That was 15 years ago, roughly.
Fabulous. The second edition just came out, as I understand. When was the first edition published?
22.
22.
Okay,
It
so
was in the same month that ChatGPT was released.
yeah, so it needs an update because a lot has
Yeah.
happened. I mean, it keeps whatever it is, it keeps improving and through iterations.
So
So
we covered GPT, not ChatGPT, but we covered GPT, the type of model, already in the first edition, just
Right.
to make this clear.
Right. Okay. Yep. So let's start at the surface level. What is the chasm between what people think these LLMs are, or AI in general, and what is it actually? Why are people's fears about it becoming an artificial general intelligence wrong? Are there literal physical structural limits in physics, in the universe, in the nature of human mind? Why has everyone got such a wrong idea? Why shouldn't we be worried about Skynet? Why shouldn't we be worried that every job on Earth is going to immediately be taken over by things that are stronger and smarter and even more creative than we are? Why is everyone all wet with these fears?
So I'll tell you the difference between what people think and what actually is by means of an analogy between a phenomenon which was quite the thing in Germany 50 or so years ago. It was a phenomenon involving a horse called Clever Hans, der kluge Hans.
100 years ago.
Clever Hans was the star of various circus entertainment shows, and people would pay money to see Clever Hans calculate before their very eyes. So you would give Clever Hans a problem to solve, so multiply 19 by 3, and Clever Hans would bang his foot, his hoof, his clop, 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 and give the answer. And everybody was amazed that Clever Hans could answer these arithmetical puzzles immediately, so they paid more and more money. But then it was revealed that the whole thing was a scam. So in fact, Clever Hans was not answering any kind of mathematical question. What he was doing was reacting to small twinges on the part of his master, when to start clopping and when to stop. Now, that means that the horse was not exhibiting arithmetical intelligence. It was exhibiting sensitivity to its master's voice. Now, similarly, ChatGPT or any of the other large language models is not exhibiting intelligence. It's exhibiting its ability to carry out various kinds of operations with mathematical algorithms. Human beings found a way to translate questions formulated in using words by people into mathematical objects. And they found a way of using the patterns in the ways people use words by collecting huge amounts of data about how people use words. And they used those patterns to generate responses to those prompts from humans, which would seem to be intelligent, relevant answers to their questions. But what's going on there is not intelligence. It's a mathematical process which has been built in very impressive ways by humans The human work here is very impressive. The work of the machine is mathematically routine. Once you have all of that data, once you have a way to extract all of those patterns, and once you have a way of using those patterns to generate responses to prompts.
Routine.
I'd like to take now, because this was one way to answer the question. I have a more abstract one that is also fully justified. That's the following. So intelligence is the ability to react to situations that are novel to the individual, completely novel, in a meaningful way to solve the challenge of the situation. And the condition is that this must happen without any preparation or training. It must be truly novel. And humans can do it for the individual, right? It must not be novel for mankind, but for the individual. And humans do this all the time. Even individuals with a low IQ do this all the time. And this is and we could not survive without this. Even animals couldn't survive without this capability. And it's embedded into a whole other set of capabilities, starting with consciousness and so on. But it's basically that is the novelty. And what LLMs do is they never do anything novel. What they do is that based on patterns that they have extracted from huge data sets, they can compute. They are sequential models, and they can compute the most likely sequence of words or picture elements based on the sequence they receive as input. This is very impressive piece of engineering, right? It's a great achievement, and it's comparable certainly to the Cologne Cathedral, for example, right? It's a huge achievement, but it has nothing to do with intelligence, because everything the machines do, they have to be prepared for by using electricity, energy worth billions, right? And also human labor to prepare the data in the right way worth billions of dollars. And that enables them to do this, which is impressive, but which is completely repetitive and has only to do with regularities. And so what are they best at? They're best at morphology, syntax, grammar. Why is this so? Because correct language is very regular with regard to the morphology and syntax. It's very irregular with regard to the content of the sentences. You can all the time formulate a sentence that is new, that has never been said before by any human being. And that happens every day, millions of times, because language is evolving, not even because of creativity, but just the normal evolution of language. But so there's the whole variance of languages which is infinite, is in the semantics and the text pragmatics of the language, but the syntax and morphology are very, very stable, because otherwise we couldn't communicate. And this stability is picked up by the LLMs because it's regular. They excel at this, but that's all they can do. Therefore, they cannot create meaningful output. Every output they create, if it gets a bit longer, contains for certain mistakes, which they call hallucinations, and is inadequate from a human perspective.
So it's perfect. I'm glad you took that tack. I want to separate in our minds LLMs, the current approach, from any other type of approach at generating AGI. So let's stick with LLMs. I want to just ask a follow-up. Are you fellows saying that it's not just a matter of adding computing power or adding a different type of training data set? You're saying they're doing something completely and utterly different than what the human mind is doing. So, I mean, am I hearing you correctly? So it doesn't matter how many more cycles you give it or how much more data you give it. It recognizes patterns in language. Very impressive. But in no way whatsoever do these LLMs think or want or do any of the things that us living systems do.
Exactly.
Okay, good.
So the technology on which they're based are called neural networks, deep neural networks, they call it. And this is a misnomer. It's a euphemistic misnomer, because the neural networks that are inside, for example, the simple fly, right, that flies around your living room in the summer, these neurons that are inside, they form a neural network, but that's a real neural network. And the real neural network has the following property. Each element of this neural network is made up of hundreds of thousands of different molecules, because it's a cell. It contains hundreds, and they interact in ways we don't understand. And these interactions then again create the interactions or participate in the interactions of the neurons, which are of chemical and electric nature, and which then create a super complex pattern that is even in the most primitive, even in Caenorhabditis elegans, a small worm, which has around 50 neurons, where we have mapped all the neurons and know exactly how they are interconnected. We don't understand at all how they work. So there is something to animate systems and their intelligent behavior, their ability to cope with novelty, that we don't understand how it comes about. And that has nothing to do with the so-called neural network that is used to create an LLM or any other machine learning algorithm. So they think that because they're connecting computational units, that therefore they are emulating the human mind. But the human mind is doing something entirely different than what Turing machines can do or do.
Right. All right. Well, let's move away from LLMs. Because you're saying that there is a fundamental impossibility to generating AGI. So I've thought for a long time, since I first saw ChatGPT and then the rest of them, that these LLMs were, if it's possible, they're going in the wrong direction. My intuition is something like, if these neural nets are anything, the way to create AGI is more evolutionary. You would have to somehow bundle up as much of the computational power as you can, build the most sophisticated neural net you can, embody it in a thing with sensory inputs, put that thing in an environment it needs to negotiate with, and then somehow embed it with the things that live at the center of our lizard brain, like hunger and thirst and the desire to procreate. And I don't know, something that would make it want to get up and start doing something rather than just sit there and be an oppressive machine. So when I think of the danger of AGI, I don't know if it's possible, but if it were going to be possible, my idea is it would have to be something like that. And then somehow the black box would bootstrap it up into a thing that is either the Terminator or Data from Star Trek. But you, smart fellows, are saying that is literally an impossible thing. So what an outlandish, ballsy claim. Back it up.
So maybe I go through the argument briefly, and then Barry can refine it a bit. So first of all, the idea of needing embodiment to create intelligence was, of course, picked up by robotic scientists already decades ago. They utterly failed so far. And why did they? Because if you want to, so we already said that intelligence is the ability to react to novel situations. And so basically intelligence is patternless. Because there is no, for the individual that copes with a new situation, it cannot recur on a known pattern. That's the very definition of intelligence. Now, we don't know how the human or the animal brain brings about this capability, but if we could actually write up how this works with mathematical equations, like you can write up how, for example, a combustion engine works with equations, then we could, and do some testing and holistic refinement, we could create machine intelligence. The point is we don't know how this intelligence comes about. But if we could, then we would be able to do that. Why aren't we? I will get back to this in a minute. But before I do, there's also another way to create, to engineer a system. That's not by explicitly writing down what it does, like in any nuclear plant or coal plant or anything we engineer, or the Hoover Dam or whatever, but by using implicit mathematics. And implicit mathematics work in the way that machine learning algorithms are trained, by taking data that describe a situation and then showing the reaction to these data by humans or animals, and then trying to configure an algorithm that it can reproduce this pattern. And that works pretty well, like spam filters trained like this. But the problem is that if a new pattern emerges that was not in the training data, the machine fails. And it necessarily failed. And because intelligence is the ability to go beyond the pattern, intelligent systems create patterns all the time that are irregular. And this irregularity cannot be implicitly trained, because a mathematical representation can always only capture regularities. That has to do with the very nature of mathematics. Mathematics is a science of regularity, and intelligence is irregular. And therefore we cannot.
I'm sorry to interrupt. Is there a way that you could, I'm trying to I'm trying to find the edges of the statement you just made. You can't. It can't discover or interact with something that is irregular. But couldn't you make its definition of something irregular so coarse that it could? I'm picturing the Stanley Kubrick's 2001 when the apes are confronted by the monolith and they've never seen anything like this before, and yet they know that to understand objects, we first get near them and touch them. And you're saying we couldn't build a computer, a robot that could, I don't know how to deal with this novel thing, but I know how to deal with things. I'm trying to grope towards a question. Couldn't we make an all-purpose intelligence that just knows I have to do these types of things to learn about something completely novel in my environment? That's beyond the pale?
No, yeah. So the problem is that the behavior that you're describing is intelligent behavior, that it is a way to deal with novelty. And you are now referring to a precondition of this, which is active perception, right? So active perception means that you can actively explore your environment by very, very complicated circuits of motor activity and sensory activity, sensory motor activity. And we don't know even how the brain does this. So we have no idea how a predator is following its prey. For example, following a prey is a basic activity. We are predators. Humans are predators. Now we don't have to hunt anymore because we have found more efficient ways to get our food, but we are by origin predators. So we have very, very sophisticated sensory motor circuitry to have active perception. We have no idea how this works. So even this precondition of intelligence behavior, we don't know how it comes about. And if we don't know how something comes about, how it's originated, we cannot build it. And the problem is that even active perception is highly irregular. So if you make movies of predator animals and then basically try to formulate what they perceive as input and then their behavior as output, you won't be able to mimic the active perception in the machine because it's so irregular. So mathematics has the boundary of regularity. And this comes from thermodynamics, and we can get to this later, but maybe I let Barry add to this now.
Yeah, so I will bring in a character called Gary Marcus. I don't know if you've heard of Gary Marcus, Adam.
I haven't, no.
So he is a leading figure in the kingdom of AI skeptics. But he's a leading figure in the sense that he's invited to sit on European Union committees to investigate regulatory measures of AI and things like that. He's written a couple of books about AI. He believes in the possibility of AGI, but he hates large language models. He thinks that they are an off-ramp towards the goal, which he thinks is achievable, of AGI. Now, so what does Gary Marcus think? Well, so I like him. He every 2 or 3 days, he has a new scandal, which he exposes in the way in which the hype underlying OpenAI, ChatGPT, and so on is manufactured. So he thinks that the way to AGI is to try to capture common sense. Now, you were getting at common sense when you talked about moving towards the object and touching it and see what happens. That's a kind of commonsensical phenomenon that the large language models sometimes break over. And now an example where they break, and these are not the large language models, these are the large video models.
Yeah, like Teslas and whatnot.
Well, no, these systems will make a video to your...
Oh, that, yeah.
So if you look at what they produce, if there is a clock in the scene, it will always say 10 to 2. And the reason is that the overwhelming number of images of clocks in the world are advertising images. And the most beautiful, attractive, symmetrical way in which a clock can show its clockiness is by saying 10 to 2. So now what does that mean? It means that all of these models, they're based always on large language models, have no idea of time. they don't understand that it's not always 10 to 2 because they don't understand what 10 to 2 might be. They just have this shape that's
Right.
very, very high in their probabilistic.
No concepts involved.
Yeah. So his idea that the way to rescue the large language models from their current problems, hallucinations and so forth, is to build them with common sense. Now, the problem with common sense is that it's not so easy to capture, because every time you think you have a commonsensical problem to solve, you will find that there are aspects of this problem which, in this particular case, are A, different from what the common recipe is, and B, very important. And then you have nothing left. So I, too, am a believer in the importance of common sense. So I mentioned earlier that I work in a field called ontology. The ontology I build, the ontologies I build are all based on an ontological representation of common sense. But I don't claim that it can be used to help people reason or to help machines reason even more. Its use is to try and make data compatible. That's about it.
I mean, what Gary Marcus doesn't get. So I think he's one of these ultimately who believe in eternal progress. He doesn't see that there are hard limits on engineering set by physics. And I think that he doesn't appreciate our argument from thermodynamics. Maybe he has even never looked at our work. I don't know. But basically our core argument is that real systems, both animate systems and inanimate systems, like the water cycle, for example, that these systems are complex systems, that the complex system properties lead to a limitation in what we can model about them. And we can very often model partial aspects of complex systems because complex systems exhibit regularities as well, like the sleep cycle, the respiration cycle, the food and digestion cycle, sexual cycle. So there are many cycles in nature, which can also the cycles of the winds, how the winds form during the seasons and over the planet. So there are cyclical phenomena that exhibit regularities that we can model, but intelligence is and also consciousness, emotions, volition, the will. All these higher capabilities are capabilities that are formed holistically by the mind-body continuum. And we think that because of the thermodynamical properties of the complex systems, there are no regularities to model. And that's our core argument. And I think Gary Marcus doesn't see this. He doesn't see that even if we could enumerate common sense, which I don't think is possible, it wouldn't help us because we still would not be able to deal with irregularities because mathematics is only about regularities.
No core regularities to model. I need to get at that a couple different ways. What is that? That's the thermodynamic limit you were talking about?
No, it has to do with so in thermodynamics arose in the 1940s the theory of complex system. Prigogine was the pioneer. He describes that complex systems have properties, and we have boiled them down into 7 properties because 7 is a nice number. You could also say it's 6 or 8, but we have defined 6 or 7 core properties that complex systems have. And I want to highlight 3 of them. One is the evolutionary nature. So complex systems are able to generate not only new elements, right, but also new element types. So for example, if an asteroid comes into the gravitational field of the sun, it becomes a satellite of the sun, like Halley's Comet, right? So that is a new element, but not a new element type. But the solar system can only have satellites of the sun as its element. So it can acquire new element types, but it can't acquire new elements. But complex systems can create new element types, right? Like bacteria can genetically change in a way that they become completely different from their ancestors. That's also true for all organisms. They can also, they exhibit a flow of energy through them that we call drivenness. So it means that they're able to create energy out of that matter and to consume this energy to live. This is actually the definition of life, is the ability to make energy out of that matter. And while this energy gets consumed, we have dissipation processes where the energy is transformed into various forms, but most importantly into heat. That's why all living entities emanate heat. and the heat dissipates then into the environment, and this creates patterns that cannot be modeled mathematically. That has been proven already in the 1940s with our inability to model turbulence mathematically. And then we have the third property, which is the most important one out of the 7 I want to mention. It's non-ergodicity. So if I take this glass of water, and I don't move the water, and I keep it the water at constant temperature, then ergodicity means now it's moving, so it's not ergodic. But if it would be completely still, the likelihood, the distribution of the particles in the water is totally regular. So no matter where I sample a molecule, the distribution of the molecules will be the same. Whereas when I spin the glass, I introduce a non-ergodicity. Now the distribution of the molecules is not the same wherever I pick a molecule set. And so this is non-ergodicity, and whenever we have non-ergodicity, we cannot infer patterns. So there is no regularity in this, right? It will always change. I can make infinitely a movie of this. It will never be at the microstate level. It will never be regular. And so that what machine learning does, it's picking examples from systems to try to identify regularities. But if what the system puts out is irregular, and that's the case with language, then the models fail. And that's why these are the thermodynamic reasons why complex systems cannot be modeled mathematically, and therefore not emulated and imitated.
I just want to play devil's advocate so I can understand exactly what you're saying. When we analyze these complex systems, we look for patterns so we can simplify what we're looking at, because we can't do the thing that, I don't know, God could do, which is look at every particle and spin and momentum and calculate things directly at that granular scale. So we look for patterns that we can model and say something about the system. But that's a limit of our own ability, not a limit of the universe.
Yes, so we have some endowments with our intelligence coming from evolution that are biological limits to what we can't do with our intelligence, and these limitations are pretty clear, and they determine very, very strongly our physics, and our physics reflect these limitations. These limitations are by no ways narrow, right? We have now space stations and gene manipulation and very fanciful technology, but they exist. And I think what we are arguing in the book, and what I think is an insight that is culturally hard to accept for Westerners, is that there are structural limits to our ability to know certain things that have to do with thermodynamics, and that these are the negative results from physics. We usually in our culture only appreciate the positive results that have created these mobile phones that we use all the time and all the fancy stuff. But we are not used to appreciating the negative results of physics. But the negative results of physics are very, very severe, and they are known to physicists, but they are not very much appreciated by lay people, including Gary Marcus, who's a psychologist.
I want to bring you in, Barry, but I have one simple question because it relates. And it has to do with certainty. Would both of you say you're 100% certain about the claims in your book about the limits of artificial intelligence? Not 99, not to the best of my knowledge, but 100%?
So I've found a new slogan, which I'm trying to practice using for questions like this. So that it doesn't matter whether we believe in this 100%. What matters is that you only ever achieve greatness through bravery. And so it would be rather boring to say, well, it may be we're wrong, but it seems like a good thing to explore. But what we say is that it's impossible. And now I'd like to come back to you and make a challenge. So you're the first person I've ever met, I think, who knows something about poker. Now, we know that the AI world is really good at finding ways of beating human beings for games like chess and Go and many video games also. But they're all closed systems, so that you can use mathematics to find winning strategies. And you can train machines to deploy those strategies. And they've done it for poker, but only for poker without visual interaction. Is that correct?
As far as I know, they haven't even bothered trying to get the computer to read their opponent. They're just using.
Right. So then this would be a very good example of a phenomenon which a brave person might say is impossible to replicate on a machine. So I then say it because I'm brave. It will be impossible to create a machine that can beat people at poker where the visual element is preserved.
Well, certainly it can beat some people. I mean, I've seen these systems, and they're pretty good. They train the no limit version, no limit hold'em versions, train against themselves and create a strategy that is game theory optimal, which you wouldn't necessarily want to deploy at a table, because what you want to do is exploit the errors of your opponents. So why play optimally when there's a strategy that does better than that? But it's very, very solid. It bluffs at the right percentage. It's aggressive. They even put them in casinos to play heads up limit hold'em. And they were so good. They came up with 3 excellent tactical systems, and it would deploy them at random. So the sucker, the customer, wouldn't know which, am I playing against the tight guy or the aggressive guy? It matters. And then those systems were winning so much money. I believe they added a 4th that was just kind of dumb, just to give the customers a chance. But they're pretty good. And just the fact that you don't know who you're playing against, it can deploy any set of tactics it wants. We get good at playing poker by recognizing who you are and how you play. And it gives me a huge amount of insight into what you're doing at this particular moment in a hand. But just not knowing what you're up against necessarily.
So does that mean that they can change their strategy in mid-game?
I don't think they would. They can probably do whatever they want, but I don't think that's the way they did it. I think they rolled a die and picked an avatar and had that one play this particular hand.
So let me check that I've understood this correctly. These are machines which are seeing what you do.
No, I mean, they know that I've bet or I've
checked, but they don't see your face or anything.
Nothing.
Okay, no. Because if they could see your face, what would happen? What would break if the visual dimension to the computer was open?
Well, it would be interesting. On the one hand, it could use its incredible database to get a good read on me, but on the other hand, I could maybe trick it.
Yes. Yeah.
I think it would do better off not trying to use that element at all and just rely on the fundamentals of the game you're talking about and just play a really, really solid strategy.
Well, Adam, let's boil this down to what's happening here. So what you're describing is that the regularities that are present in poker can be perfectionated with machines, and that's true.
Yeah.
But the irregularity that happens by the human interaction can't. Now, and also poker is of course taking this acting part aside. It's a closed system.
Yeah,
it only becomes an open system game. Yeah, so it's not such an informative example.
I agree. It's only 52 cards. It is a closed system as far as I'm concerned.
I would like to also answer your question. So I'm completely certain that we will never be able to mechanistically understand intelligence.
Okay.
And because I'm also 100% possible, like Immanuel Kant said, that we cannot mechanistically describe the growth of a blade of grass, which is also biological animal system phenomenon, and in the same way, I don't think we can mathematically describe how thinking works, which is of course much more than intelligence. It's many capabilities working together to enable what we analyze and call intelligence, and therefore I don't think we can build it. Neither can we obtain it, and I'm also 100% certain by trying to imitate the human, because whenever we act in an intelligent manner, we deviate from the pattern. So I'm 100% certain.
The skeptic would now say, but you're just drawing conclusions from present day mathematics.
Yeah,
how can
I agree to this, but I would say that given the history of mathematics, what we can say for sure is that mathematics is all about regularity, and that the limits that we encounter in thermodynamics, of which we know, come from the discrepancy between the regularities needed for mathematics and the irregularities, the fundamental irregularities of complex systems. So this is my argument. And of course, mathematics is continuing to evolve, and it will become even more beautiful and complicated. It will be harder and harder to find new aspects, by the way, because you need to. The examples of recent proofs show that you need to have more and more knowledge of very different disciplines of mathematics to come up with new proofs. So it's getting really fascinating, and it will continue, but it's always working with regularities. And so that's I think that's why I feel so certain about what we're saying. It's not only because I think an effect can only be achieved by being bold, which is true, but also because I fundamentally think that we have discovered here a way to apply the negative results of physics to a very important question of our time.
Now define regularity.
I mean, regularity is a pattern that gets repeated. It can be very, very complicated, but it's a pattern that gets repeated, and that ultimately every equation that we can have describes such a pattern by relating the two sides of the equation to each other.
So is the content of Tolstoy's War and Peace, which exists in millions of copies, a regularity?
I mean, there's a regularity pattern, of course, that all the copies are in a way isomorphic to each other, right? So even if I have a German translation, it's to some extent isomorphic to the Russian version, though it is of course not the same. But or not isomorphic, but homoeomorphic. So it's similar, right? But of course, within Tolstoy's novel, it's fundamentally irregular. It's one of the greatest works of art ever written. It analyzes human beings in a surprising way. You are unprepared, like the scene how she behaves. Sorry, you were saying War and Peace. I'm now referring to Anna Karenina. How Anna Karenina behaves in the opera, the scandal she creates. This is typical of totally the irregularity of human behavior. So actually good novels, Le Rouge et le Noir by Stendhal, Faubert's Madame Bovary, all these great novels are all about fundamentally irregular people who behave in a very, very surprising way, as you would never have predicted it. And I think
I'm sorry. I want to get back to the various ways you're saying this. We don't have anything to worry about with AGI.
Mm-hmm.
But I want to ask a slightly, maybe it's on topic, maybe it's off topic, but I think it'll be revealing. I assume that both of you would reject the position of hard determinists.
That's one of the things which are beyond the limits of what we can know.
Right.
So what we say in the book, in chapter 3, I think, where we talk about the monism we believe in, is that we believe that there are laws of nature that kind of that are present, the four fundamental forces of physics that determine everything that happens, but that we don't know how this happens, right? So we believe that the human mind produces our experience because there are physiological processes going on that create our consciousness and everything that pertains to it, but we don't know how. So of course, the answer that Barry was giving, I completely subscribe to it, and it's also one of the three antinomies of Kant. Kant says we cannot answer the question whether we have a causally determined world or not, and I agree to this.
Yeah, I'm lying in the same place. The determinist's argument is a very simple one, easy to understand, but since we don't understand our own consciousness or how the universe works at a fundamental level, since it seems like we have free will, I think epistemologically it would be crazy to reject that until someone were to put you in an fMRI scanner and then print out everything you're going to do for the next 2 weeks. And gosh darn it, that's exactly what you did. Am I correct in the book that you say that systems of the sort that are human intelligence literally cannot be modeled such that they will run in a computer? Is that a true statement?
Yeah.
And how and why? What limit are they? What limit is why won't the thing fit in the box? What's going on that you can't model that way?
There are a dozen reasons, but the question is, how would you do the fitting? And there are various alternatives. One alternative, which we go through in great detail in the book, one alternative is to try to emulate the brain by working out what the structure of the brain is, and then copying it in some fine-grained physical model. And the problem is, in order to find out how the brain is working at any given time, you have to do imaging. And the quality of the imaging that we have is very low resolution compared to what would be needed in order to see exactly what's going on inside any given neuron or in any given synapse, to such a degree that it's absurd even to expect that we could ever reach the appropriate level of resolution. But even more, in order to capture what's going on dynamically at any level of resolution, we would first need to kill the patient. And that is probably going to be a bit difficult to...
Well, there are certain regimes in the world by which...
And then another way of doing it would be to simulate evolution. So we can get computers to play chess games with themselves thousands of times a minute so that they can build up a knowledge of all possible strategies and all possible outcomes and so on. You can do that with any closed system game. So why don't we do it with evolution? Why don't we build a model of evolution starting with tiny models of proteins and amino acids and so forth, and watch as it evolves inside the computer into a representation of what happened in evolution. And the problem here is that we have no idea about how evolution happened. We have very little data. Most of the data about evolution is long since unobtainable. But most importantly, the problem of evolution is way more complicated than the problem of intelligence. So if we can crack evolution, that would mean that we'd already cracked intelligence much earlier than that. Intelligent action is part of what brings the evolution about.
So another very old argument is two very old arguments why we cannot fit intelligence in a box. Is the first one is that even if you were able to model mathematically intelligence, that would not necessarily mean that it can be that this mathematical solution can be formulated in the form of Turing computable functions, because Turing computable functions are only a rather small subset of all possible functions. And so this is also an important argument that is often overlooked. The second one is the incompleteness argument, Gödel argument, essentially, that you say if you have a mathematical system, you have this incompleteness problem. So, I think that what we see is that even first order logic is not Turing decidable. It's semi-decidable, they say, but you can very easily formulate a problem first order logic that lets the computer compute forever, whether to assign a truth value to the problem. And this is in a very artificial setting with low semantic expressiveness. First order logic is not very expressive. It's expressive enough for the mathematics because mathematics is so regular, but there's no natural language text that you can translate into first order logic without massive loss of meaning. And so, you can create artificially such text, but you can't translate any philosophical work into it. You can't translate a textbook of chemistry into it. So it's a very, very restricted formalism. Even this one is not fully Turing computable. Only it's actually undecidable. And so this is even much worse if you get into other areas. So it's just that the functionality of a Turing machine is rather limited, and I think this limitation is very often not seen because people are impressed by what they see, what computers can do, but they then don't think through properly that this doesn't mean that they can do everything, right? And so in the end, the recursive functions that are computable are much too limited to mimic what the human mind or the animal mind can do.
Here's an argument I figure you fellows don't like very much. What do you think about the anti-human argument that the more we learn about these AIs and their limitations, we're not really discovering the limitations of these machines. What we're really discovering is just our own limitations. Maybe we're just fancy LLMs. I mean, you've heard people say this, I assure.
I subscribe to everything you just said, but the final statement, maybe humans are fancy LLMs. No, what we learn by looking at these models is a limitation of implicit mathematical representation, and that's one of the core arguments of our book, right? That basically, if you look at how how machine learning works, and even future machine learning algorithms that we don't know about yet, we see by very good example is how they represent images, right? So inside an LLM, the image is turned into a Fourier space representation, and then the machine is using this representation, which is a dimension reduction of the image properties, to classify it, for example. That's very error prone because it doesn't utilize what we use to classify the image, but something entirely different that has nothing to do with human cognition. So what we learn by looking at this is indeed the limitations of what we can engineer. But that doesn't mean that we are very limited and work ourselves like LLMs. It just means that our endowment, our biological endowment that is called mathematics, has limits, which is actually must be the case since our brain is limited in size and complexity, right?
So I just want to add one footnote to what Jobst just said, because I think this is one of the most original aspects of our book. So it relates to the history of mathematics. For a long time, mathematics was always explicit. So mathematicians would write things on paper, cross things out, and eventually they would have proofs, and everything was explicit. You could see it. And that was a limit on what could be achieved mathematically. Some of the ideas that they had in the realm of explicit mathematics cover the knowledge which is used in present-day machine learning, but they couldn't exploit that knowledge because they only had pen and paper. Now we have implicit mathematics. And what implicit mathematics allows is that we can use gigantic bodies of data which we press into a device, and the device turns those data into algorithms. And that's what an LLM is. It's just a shockingly big algorithm which converts a prompt into a response deterministically.
Right.
Although sometimes they fiddle so that it doesn't appear deterministic. And so we don't know the limits of implicit mathematics yet. But we do know that the limits can't go beyond Turing computability because these are machines.
And beyond regularities.
Yeah.
So these are the two big. So I think the limitation by regularities is the bigger limitation. Then the secondary limitation is the Turing computability. But Turing computability is not the core argument. The core argument is a irregularity, the fundamental irregularity of complex systems. And let me give you another example that is very informative. If you go to school and look at an orrery of our solar system, you think it's completely regular, and then you can program it, the modern ones that it can simulate perfectly past solar eclipses with all the planets and the moon in the right place and so on. And it's very impressive because you see the shadow cast by the moon onto the sun, onto the earth and so on the orrery. And then you believe, but then my physics teacher already told me when I was 16 or 15, but there's something that the orrery cannot represent, and that's the wobbling movement of the Earth on its orbit. And the wobbling movement comes from the irregular forces of the other planets exerted on the Earth. And we cannot model this. We have no clue. There's no way to model it. We cannot, even by observing this wobbling for a long time, we can figure it out. There's no regularity in this. It's an irregular pattern that is beyond physics, he was saying. And at the time, I remembered it, but I stored it in my brain without fully realizing what it means. And many, many years later, when we wrote the book, I remembered it again, right? And so this wobbling is an irregularity that we can't model. And the nice orbits drawn by Galileo and Newton, they abstract this away. But the wobbling can be observed and measured, and it's totally irregular. There's no way to model it. No AI model can predict it, even if we record it for millions of years and feed all the data into the model. And I think these are the kinds of things that you have to consider when you think about the relationship of mathematics and nature.
Yeah, so
we are nature.
The wave example is another case.
Yes.
So there are billions of waves coming on every beach in every day, and no two of those waves are identical. They're all wobbling.
They're all wobbling.
Yeah, the microstates, their microstates are always differing. And so if you want it, and of course you can create with AI, now you can give a prompt and say, show me a wave pattern on a beach. And the macrostates will look kind of all right. You will notice that it kind of loops and it doesn't really look totally natural, but it's still quite good, right? But if you go to the microstate level, no chance of emulating it. And so this is the point. And
The skeptic would say this is a limitation of our ability to observe or our ability to model. Newton was slightly wrong. Einstein improved. We don't understand what the heck's going on with quantum mechanics. We're just not there yet, they would say. And once we do understand and can observe and model correctly, we will understand why the wobble wobbles and how each unique wave crashes on every beach, and all will be known.
Yeah, but then this person has failed to appreciate the negative results of physics. He has only appreciated the progress, the bright part of physics. But physics has a shadow part, which tells us about what we can't do with physics, and it's huge, right?
Yeah.
And if you really go into the theories of physics and take the time to appreciate them carefully, which I'm not a physicist, but as a mathematician, I was able to do it. I did this during COVID, by the way. That's also improved the book in the second edition. And then when you dig into it, you discover all of these problems. And then especially you are, and this we were already capable before COVID, you basically are able to appreciate the negative results from physics. And these results are very important. And such a techno-optimist or physics optimist, he would probably, if you confront him with all these limitations at a detailed level, he will also be unable to cope with it. And I think this is just a matter of intellectual honesty. And so I believe, and that's a very important point we haven't discussed yet, I believe that our culture is in some way dishonest because we pretend that we can do things that we can't do. And it leads also to waste of resources. So it's better to focus on doing projects that are feasible. And we have to accept that some things are not feasible, and then we can just relinquish on them and just not do them and focus our resources on other things.
I feel like this has been a very scattershot interview in discussing your book. I apologize for that. I want to end on, I believe you make the argument in the book that simulation theory is all wet for similar reasons. But before we get there, is there any other great set of arguments you lay out in the book that I've hopped over that you'd like to flesh out for us here?
I think simulation, actually.
All right, well, let's go right there.
To suggest that we talk about that topic.
I think Nick Bostrom and Elon Musk are absolutely nuts when they talk about the probability that we live in a simulation already.
Yeah.
It's hard to form probabilities when you have a data set of zero simulations that are indistinguishable from the perspective of those inside it. But that's a gambler's perspective. I think you're talking about something much more fundamental. So
no, probably not. But are you familiar with David Chalmers?
Name's familiar, but no.
So he's probably the most famous contemporary philosopher. He's good at marketing. I think he's a clever man. He's done all kinds of good things. But his latest book is called Reality Plus. And in this book, he describes himself as a techno-philosopher. And he describes, he has the Musk kind of simulation argument going on. But the interesting story is the following. So we can assume, like many of the AI gods, wants to be immortal, which means they want to live forever in digital form in the cloud. And so Chalmers addresses the issues involved in this goal of being immortal. And so his conclusion goes something like this. We have physics. Physics is moving along very well. There are no limits. It's just a matter of pushing through until we get perfect physics. And probably AGI will help us to improve our physics. And we'll reach a point where we can create a perfect physical model of reality. When we have this perfect physical model of reality, we can build a computer which realizes this perfect model in virtual digital space rather than in the messy world here outside. And then we can make that physical model better than the world in which we live. For instance, no cancer, everybody is beautiful, and so on. And then we can offer people the opportunity to go into this model, abandon their worldly form and adopt a digital form in an improved world, and they can't complain or hesitate because it's a perfect model of reality which they're in anyway, only better.
So the key problem of this argument is that it's a very crude form of Cartesianism, and that the key statements that he makes, the key assumptions that he makes are wrong from the perspective of physics. For example, he says everything can be described with quantum physics, right? And therefore, if we apply quantum physics well enough, we can then describe the world perfectly. Now, he's disregarding two results of physics. The first one is that gravitation cannot be explained at all with quantum physics. So there's one fundamental force that of the four forces that is super important that we have no idea about how to explain with quantum mechanics. And then the second problem, he's of course not thinking of the multiple particle problem. So even in classical physics, in classical mechanics, when we have many particles, we don't have good models anymore because the interactions, the gravitational interactions of the many particles make it impossible. So then we have to simplify and work with fields, but we have to make many simplifying assumptions to define the fields. And that's also true in quantum mechanics, and every physicist knows this. Therefore, the models of quantum mechanics apply to many particles. The quantum field theory is interesting, but it's very rough, and it can only describe certain properties of, for example, of relatively homogeneous matter, where certain assumptions of regularities between the constitutions, the elements of a body hold, and so on. And all of these limitations he doesn't even know about, though he studied physics. So it's very strange why he doesn't have a clue about this. He has a very naive picture of physics, actually. And then he comes to this Cartesian, it's like a very crude Cartesianism about the world, and it disregards totally that even physics itself rests totally on metaphysics. You cannot even explain the measurement scale without metaphysical assumptions. You cannot explain, for example, the question, why can you obtain laws of nature by induction? In the end, a question that is not answerable philosophically, but it's a metaphysical question. All of this, he totally takes out of the picture. It's a very depressing in its naivety. It's very depressing to see that somebody can create such a theory and be taken seriously, while it's so obvious that he is just lacks very simple basic knowledge of physics that every undergraduate student learns.
It was a bestseller.
Yeah. And so we believe that this is pure nonsense and just reveals ignorance. It's really and I think actually that all the AGI proponents that really proclaim that we are going to have singularity, for me it is really a matter of either ignorance or intellectual dishonesty or mixture of both.
I suspect you're right, but how does what you just said interact with the idea of Neo in the Matrix, or us taking a brain and putting it in a vat and connecting it with various sensory stimuli such that it thinks that that is the nature of the universe?
So to
is
begin
such a
with,
thing possible, or?
Yeah, so to begin with, the way we perceive the environment is always based on sensory motor perception, active perception. And we don't know the patterns that active perception creates. So of course, there are electromagnetic phenomena that explain how our senses work. But the patterns, when I, for example, hear myself while speaking or see my mouth moving while speaking, there's an internal feedback loop. And this pattern, we don't know this pattern. We can't measure it. So if we can't measure this pattern, we cannot create the impression of the pattern that emerges from active perception. So we cannot have Neo in the vat, because we just don't know which stimuli to give to the brain to create the impression that we have. But if we do it, if you put on these goggles for VR, you get nauseated, right? Or many people get nauseated because it's the wrong pattern, obviously, to create spatial impression of space. That's why VR never took off, because most people get nauseated by it. Because it's.
Are you sure it's most? I have one of those Oculus, and I don't like to use it for more than half hour or so, but I don't get nauseous.
Yeah, but somehow it's okay. 30% get really nauseated, okay. But even the rest who don't get nauseated, they feel that in the longer term, it's not the adequate stimulus. So in physiology, you're talking
For
about
sure.
adequate stimulus, and it's not an
For
adequate
sure.
stimulus. And that's because we don't understand what the adequate stimulus looks like.
But what would happen if we just fiddled around and tried various things until thousands of iterations later we just sort of stumble upon the correct stimulus response for motor feedback?
We would then have it maybe for one certain special situation. But again, because of the irregularity of active perception, because active perception is itself deeply irregular, we could never go through all the permutations by trial and error. This is the key argument we are using.
What are you doing in those 30 minutes when you have the goggles on?
I haven't fiddled around with it for a couple of years, but there's games that are entertaining.
I see.
I mean, I see you celebrating there, Jobst, but it's not that I don't like it. It's just I enjoy video games, and I haven't played one since I started podcasting and writing because I'm busy. I'm more interested in other things, but I do enjoy the simulated worlds. I just don't think there's any reason to think we live in one. I think that's a ridiculously bold claim. I am very grateful for your time, gentlemen. Before I let you go, what didn't I ask that is relevant that you want to expound
So I'd like to give my answer to the Fermi paradox.
Okay.
You know what the Fermi paradox is?
Yeah.
Where are they? That's the idea. So, and the argument why we should be seeing aliens goes like this. So there are so many planets on which it's possible that there are intelligent beings, and intelligent beings are going to explore, for instance, interstellar exploration. And so eventually we have to start seeing evidence of it if only by devices which crash into the Earth. And the reason why we never see it is because it's not because there aren't enough such planets. The probability says that there are. The reason is that there are absolute limits to intelligence. And these absolute limits apply not merely to Earthlings, they apply in general throughout the universe. That's one of the consequences of our book, or one of the ways in which you can read our book.
I think
in the gap.
Yeah, when you look at how Stanislav Lem, famous science fiction author, deals with the phenomenon, he has a different theory, which is much less convincing. And I think the theory of Barry that it's just that intelligence cannot create certain things systematically because it's itself only a biological capability, right? That is limited by the way that matter animate systems can work is brilliant. And what I would like to also answer your question by saying, what we didn't discuss very much is, or in detail, and what is new to this edition of the book are two things that we also didn't talk about. One is the physics chapter, which is chapter 7, which really gives a very sober view of the limits of physics and prepares the reader for the overall argument and points the reader to appreciating negative results from physics. And we use for this purpose two very, very good female theoreticians of science, Nancy Cartwright and what's the other one, the German one, Barry?
Brigitte.
Yes, Brigitte Falkenburg. And this is what I would like to point listeners to. And then the other aspect is that we have now talked in the new edition quite a lot about personal knowledge and practical knowledge, practical intelligence, which was Barry's idea. And because he comes from a philosophical tradition to which this matters a lot, phenomenological movement, to which I also belong, which is also basis of our friendship. And readers can also read a lot about this in the new edition. And I think these are two aspects we didn't discuss today that are very interesting, also beyond the arguments the book deals with. That's what I would like to add.
Fascinating. I approach the Fermi paradox in this, like everything I look at is through the lens of a gambler. I'm not impressed with the simulation theory because we have 0 data points for creating a simulation we can't tell we're in. At least with the Drake equation, there's one data point, us. But I think that the Drake equation is supposed to tell us about the probability of life in the universe is just nonsense. We don't have the slightest idea what the requisite properties are of life originating anywhere besides us. So it's just a lie upon a guess, upon an assertion, until we're so confused. Oh, hey, that was an exponent. I guess this must be science. So I just say you know, if an alien species ever shows up, okay, great, I'll start changing my assumptions. But I see no reason to assume that there is any other life until we discover it, let alone intelligence.
Yes.
We understand so little about what intelligence is. You're going to show me an equation and tell me what percentage of the universe has it? Come on. Again, gentlemen, thank you so much. I like the way both of you gentlemen think. I want to encourage people to purchase and read this here book, Why Machines Will Never Rule the World, because we don't want to fear artificial intelligence. It's just a stapler that can write a filthy limerick. Why in the world should we be afraid of that? Thanks again, gentlemen. I hope to speak to you again because you're both very smart fellows.
Thanks, Ed. It was a big pleasure. Bye-bye.
We'll see you next time on Haman Nature. Bye-bye.